When we are given a linear system of equations, the main thing that we want to solve for that system is the point of intersection. So if you were given an equation as follows, 3x minus 1 equals 5x plus 2, and you were asked to graph it, what you would be solving for graphically is the point of intersection. We want to know where 3x plus 1 will intersect with the equation of 5x plus 2. But, however, we're not always going to be given the option to graph the two equations in our linear system. So instead, we can try to solve for the point of intersection using algebra. There are two different methods that we can use to solve a linear system of equations. And the first method that we're going to focus on in this video is a method called substitution. So here in our example, we have a system of linear equations. We have one equation, y equals x minus 1, and a second equation, y equals 3x plus 5. The first thing that we want to do when we're given a system of equations is number them off. So I'm going to call this equation number 1 and this equation number 2. When I look at my equations, I see that both equations are in the format y equals mx plus b. So what I notice then is that the first equation is set up with y equals, and the second equation is also set up with y equals. In the first equation, they're telling us that x minus 1 is equal to y, and in the second equation, they're telling us that 3x plus 5 is also equal to y. So both of the equations are equal to y, which means that the equations are essentially equal to each other. So what I can do is take equation number 1, which is x minus 1, and I can set it equal to my second equation, which is 3x plus 5. So now what I've done is I've set up a system of equations where there is only one variable for me to solve, and that would be the letter x. So like we know what to do, we can take our like terms and collect them. So it doesn't matter which side you choose to put the variable. You could put the x's on the left side or on the right side. So I'm going to bring my x terms over to the left-hand side. So that means that this 3x needs to come over to the left. And I'm going to collect all my constant terms, or just the plain numbers, and I'm going to collect them onto the right side. So that means this minus 1 needs to come over to the right-hand side. So if I collect like terms, I would get x minus 3x is equal to 5 plus 1. So x minus 3x is negative 2x, and 5 plus 1 is 6. And then I can isolate for x by dividing both sides by negative 2. So that gives me a solution of x equal to negative 3. So if you recall, a point of intersection has an x value and a y value because it is, after all, a coordinate point. We've so far solved for the x value. We now need to go ahead and solve for the corresponding y value. So what I can do is I can take my solution for x and substitute it back into either equation number 1 or back into equation number 2. It does not matter which equation you choose, your answer for y should still come out to be the same. So I'm going to choose to take my x value and substitute it back into equation number 1. So I'm going to make a note of that here. I'm going to substitute x into equation number 1. So equation number 1, I'm going to recopy it. It is y equals x minus 1. But I know what my x value is. We calculated it to be negative 3. So in the place of x, I'm going to substitute negative 3. And then I'm going to do the math. Negative 3 minus 1 is negative 4. So therefore, I know the point of intersection for this system of linear equations is located at negative 3 and negative 4. Okay, now it's your turn. We have another system of linear equations set up just like the example that we just solved. So you should take this time now to pause the video, try seeing if you can find the solution, and then when you feel like you're ready, you can come back to the video and hit play. Okay, so the first thing that I did as part of my solution was to number off my equations. So I took the first equation, y equals minus 2x, and I call that equation number 1. And the equation y equals 4x plus 6, I just called that equation number 2. When I look at how the equations are set up or laid out for us, I noticed that both of the equations are set equal to y, which means that they are essentially equal to the same thing. They're both equal to y, which means that they are both equal to each other. So I can just take equation number 1 and set it equal to equation number 2. What I now want to do is collect like terms. So I'm choosing to collect all of my x terms over on the left-hand side. So I'm going to bring 4x over, which leaves me with negative 2x minus 4x, which is equal to 6. Negative 2 minus 4 is negative 6x. And then to isolate for x, I'm going to divide both sides by negative 6. So that leaves me with a solution of x equals negative 1. Now that we have our answer for x, we need to go back and solve for y. So it is your choice to take your x value and substitute it back into either equation number 1 or equation number 2. Since we used equation number 1 in the previous example, let's just maybe change it up and substitute x into equation number 2. If you chose to substitute x into equation number 1, that's fine. You should still come out with the exact same answer at the end. So I'm going to recopy equation number 2, which is y equals 4x plus 6. In the place of x, I'm going to substitute our answer, which was negative 1. And now I'm just going to do the math. 4 times negative 1 is negative 4. And negative 4 plus 6 is 2. So our answer for y is 2. So we can say, therefore, the point of intersection is located at negative 1 and 2. So what if the equations looked like they did below? How could we now solve for substitution? So if we look at the equations, we've got 3x plus 2y equals 1, and a second equation of y equals 3x plus 5. So the second equation looks like what we just saw in our earlier examples. It is an equation that is linear and in the correct format of y equals mx plus b. The first equation, however, looks a little bit different. It is clearly not in y equals mx plus b format, and that's okay. To solve for a point of intersection using substitution, the equations do not have to be in y equals mx plus b format. It does, however, make the substitution a little bit more trickier because we're going to have to do a little bit of rearranging, but nothing too crazy. So if we were given a system that looked like this, the steps would be to isolate one of the variables in one of the equations. You would then substitute that new equation into your other equation that you didn't rearrange. You would solve your equation for your variable, and then same like we did before, you would take your answer and your choice to plug it back into equation number 1 or equation number 2. So let's take a look at that very same system. We've got our equations here. Same like we did before, I'm going to number them off, number 1 and number 2. So if I look at my two equations, I want to start by looking for the equation that seems to be the simplest. So that to me, when I look at the equations, would be equation number 2. And I say that this is the simpler equation just because I know that it's already in y equals mx plus b format, and it happens to have the letter y already isolated. And what I mean by that is the letter y is by itself on one side of the equation, and the other two terms are together on the same side. Because equation 2 is already isolated for y, what I know is that wherever I see the letter y, I know that it is equal to 3x plus 5. So what I can do is I can take this portion and I can substitute it or stick it into equation number 1 in the place of y. So I'm going to start by substituting equation 2 into equation 1. So I'm going to recopy equation number 1. So I've got 3x plus 2y, except in the place of y, I'm going to put in equation number 2. And equation number 2 is 3x plus 5. And then equation number 1 ends with equal to 1. So I've taken equation number 2 and I've stuck it or substituted it into or inside equation number 1. So now we're going to take what we know about solving algebra, and when you have a whole number in front of a bracket, you are going to need to distribute. So I'm going to take 2 and distribute it into its bracket. So we're going to recopy 3x. And if I distribute, I'm going to have 2 multiplied by 3x, which is 6x, and 2 multiplied by 5, which is positive 10. That is all equal to 1. So I notice that I have some like terms here. So I'm going to choose to collect like terms first before I start moving things over. So 3x plus 6x is 9x. I still have my 10, and I still have my 1. So now if I choose to collect like terms, I'm going to take this positive 10 and move it over to the right-hand side. So that's going to leave me with 9x equals 1 take away 10. If I do that math, I'm going to get 9x equals negative 9. And then we're going to isolate for x by dividing both sides by 9. So that leaves us with x equals negative 1. So I have my answer for x, and now it's my choice. I can take my answer for x and choose to substitute it back into equation number 1, or we can put it back into equation number 2. I'm going to choose to substitute it into equation number 1. So I've recopied equation number 1, 3x plus 2y equals 1. And now in the place of x, I'm going to put in my answer, which was negative 1. I'm going to recopy the rest. 3 times negative 1 is negative 3, plus 2y equals 1. Okay, I'm going to go ahead and collect like terms. So I'm going to take this negative 3 and bring it over to the right-hand side. That's going to leave me with 2y equals 1 plus 3. 1 plus 3 is 4. And then I'm going to isolate for y by dividing both sides by 2. So that's going to leave me with y equals 2. Okay, so therefore my point of intersection for this linear system is located at negative 1 and 2. All right, now it's your turn. We have a brand new system of equations. They are set up exactly like the previous example. So I would take the chance now to pause the video, try solving this system on your own, and then come back to the video when you think you've gotten an answer. So the first thing you want to do is number your equations. So I've numbered the first equation with 1 and the second equation with the number 2. I noticed that in my second equation, it is already isolated for the letter y. So what that means is I can take my second equation and substitute it into the first equation in the spot for the letter y. So I'm going to make a note of that here. I'm going to substitute equation number 2 into equation number 1. So I'm going to recopy equation number 1, 4x plus 6y equals negative 18. But in the place of the letter y, I'm going to replace it or substitute it with equation number 2. So that's going to be the x plus 7. And that is equal to negative 18. So now I am going to distribute. So that's going to give me 4x plus 6x plus 42. 6 times 7 is 42. And that's still equal to negative 18. So I have some like terms here with my 4x and my 6x. So I'm going to put them together. That's going to give me 10x. And then I'm going to recopy the rest. Okay, I see that I can take my positive 42 and bring that over to the right-hand side to collect those like terms. So that's going to leave me with 10x equals negative 18 minus 42. Okay, if I do that math, I'm going to take negative 18 and subtract 42, which is going to leave me with negative 60. And then to isolate for x, I'm going to divide both sides by 10. So that leaves me with x is equal to negative 60 divided by 10, which is negative 6. So there's my answer for x. And then from this point, it is your choice. You can take your answer for x and substitute it back into equation number 1 or into equation number 2. So at this point, I've chosen to substitute my answer for x back into equation number 2. So I've recopied equation number 2, which was y equals x plus 7. And in the place of x, I'm going to put in my answer for x, which was negative 6. And then negative 6 plus 7 is a positive 1. So my answer for y is 1. So I can say, therefore, the point of intersection is located at negative 6 and 1. All right, in our last example, if I take a look at the system of equations on the screen, the first thing I notice is that neither of these equations is in the format of y equals mx plus b. That's not a problem because, as I've mentioned, the equations do not have to be in that format in order for you to solve. Okay, the other thing we want to check for then is any of the equations set up where one of the variables is isolated, or in other words, is one of the variables on its own. So when I look at the first equation, I see that x and y are on the same side. So this equation is not isolated for any particular variable. When I look at my second equation, I also see that x and y are on the same side. So this equation is also not isolated for any particular variable. So it now becomes your choice. You can take either of these equations, number 1 or number 2, and you can choose to isolate for one of the given letters, either the letter x or the letter y. It's going to be completely your choice and whatever your personal preference is. My suggestion is, though, to always look at your two equations and try to pick the equation where there is a variable that does not have a coefficient or a number in front of it. So when I look at the first equation, I notice that x has a 2 in front of it and y has a 3 in front of it. It's not a huge deal, but just to keep the math really nice and simple for myself, I want to look for the equation, if possible, where there is a variable that doesn't have a coefficient in the front. So when I look at the second equation, I notice that the y has a 4 in front of it, but the x does not have a number. We do know that there is a number 1 in front of the x, but it doesn't have a value greater than 1. So this is the equation number 2 that I want to work with. So I numbered off my equations 1 and 2, and I've decided that I'm going to work on rearranging equation number 2. So when I say I want to rearrange it, what that means is I want to get x by itself. So I want to isolate equation number 2 for x. So that means to get x by itself, I need to take this positive 4y and just move it over to the other side. It doesn't want to be anywhere near the letter x. So if I move that positive 4y over, that's going to leave me with x is equal to 6 minus 4y. So now I've created another equation where x is completely isolated. So what I'm going to do is I'm actually going to call this equation number 3. So now that I have this equation isolated for x, I know that wherever I see the letter x, I can replace it with 6 minus 4y. So what I'm going to do is I'm going to take this expression, 6 minus 4y, and I'm going to substitute it in the place of x in equation number 1. Okay, so we're going to sub equation 3 into equation 1. So I'm going to start by recopying equation number 1, 2x minus 3y equals 1. And now in the place of x, I know that I can replace it with 6 minus 4y, because I'm substituting equation number 3 into equation number 1. And there's that portion right there. So I'm going to start off by distributing 2 into the bracket. So that's going to be 2 times 6, which is 12, minus 2 times 4y, which is 8y, and then I'm going to recopy out the rest. So I see that I have some like terms that I can put together. So I see that I've got a negative 8y and a negative 3y. So I'm going to start with that. So I've got 12, and then negative 8y minus 3y is negative 11y, and that's all still equal to 1. So now what I'm going to do is I'm going to take this positive 12 and I'm going to bring it over to the right-hand side. So that's going to leave me with negative 11y is equal to 1 minus 12. So negative 11y is equal to negative 11. And then to isolate for y, I'm going to divide both sides by negative 11. And y is going to be equal to 1. Same like before, we're going to take our answer for y, and we have a choice to plug it back into equation number 1, equation number 2, or if you really wanted, you could plug your answer into equation number 3. Now, if I actually go back and look at my equations, equation number 3 would be the fastest and best option because equation number 3 is already set up to solve for x, and x is the letter that we want to solve for. We've already gotten an answer for y. All that's missing is an answer for x. Now, you don't have to use equation number 3. You could totally choose to take your answer for y and plug it back into equation number 1 or equation number 2. So I'm going to choose to plug my number into equation number 3. So I'm going to recopy equation number 3, which was x equals 6 minus 4y. And in the place of y, I can put in my answer, which was 1. So if I solve, I'm going to get 6 minus, and then we've got 4 times 1, which is 4. 6 minus 4 is 2. So just be careful. We did solve for the letters a little out of order, which is totally fine, but students tend to mix them up when they plug them back into their final answer when they're telling or stating what their point of intersection is. So when we write our final therefore statement, we're going to say, therefore, the point of intersection is 2 and 1. Remember, your x value always has to come before your y value. All right, now it's your turn. Here is another example with a linear system. You do need to rearrange one of the equations to isolate for a particular variable, your choice, x or y. So pause the video, give this question a try, and when you think you've gotten the solution, come back to the video. All right, so the first thing I did, like always, is I numbered off my equations with number 1 and number 2. The next thing I want to do is look at the equations and try to figure out which one would be the simplest to rearrange or isolate for a particular variable. So when I look at equation number 1, I notice that both x and y have numbers in front of them, or numbers that are not 1. So if I do try to isolate for x or y in this particular equation, there will be some extra steps and I'll have to divide to get rid of those numbers. It's not going to be super pretty. So when I look at equation number 2, however, I notice that my x only has a coefficient of 1 in front of it. There's no other number in front of that letter x. And the same thing actually goes for y. Okay, there is no other value in front of the y other than a 1. So number 2 is definitely going to be the easiest to rearrange and manipulate, and it doesn't really matter which letter I choose to solve for. I could choose x or I could choose y. So I'm going to choose to take equation number 2 and I'm going to isolate for x. So I want to get the letter x completely by itself. So I'm going to take this negative y and move it over away from the x. And I'm going to do the same thing with this negative 2. I'm going to move that to the right-hand side and get it away from the x. So if I move those things over, that's going to leave me with x equals y plus 2. Okay, the order doesn't matter. You could totally say x equals 2 plus y as long as you get one variable by itself. So this new equation that I just generated, I'm going to call it equation number 3. Okay, so that tells me that in equation number 3, I know x is equal to y plus 2. So that tells me I'm going to take this portion and I'm going to substitute it back into equation number 1 wherever I see the letter x. So I recopied equation number 1, 2x plus 3y minus 9 equals 0. And now in the place of x, I'm going to substitute equation number 3, which was y plus 2. And then the rest just gets recopied. I'm going to now distribute 2 into its bracket. So that's going to give me 2y plus 4 plus 3y minus 9 equals 0. So your choice, you can collect some like terms on the left-hand side first, or you can choose to start moving things over. So I noticed that there are lots of like terms on this left-hand side. I've got a 2y and a 3y, and I have a 4 and a negative 9. So I'm going to start by putting together my y's. So I've got 2y plus 3y, which is 5y. Well, that's got to be a little bit darker for you. And 4 minus 9 is negative 5. Okay, so now I can separate my terms. So I'm going to take this negative 5 and bring it over to the right-hand side. So that's going to leave me with 5y equals 0 plus 5. 0 plus 5 is just 5. And then I can isolate for y by dividing both sides by 5. So that's going to leave me with y equals 1. And now your choice, you can take your answer for y and substitute it back into equation number 1, equation number 2, or your choice, you could even put it into equation number 3. So equation number 3 would be the best because it is already set up to solve for x, but I'm going to change it up, be a little bit different, and I'm going to choose to substitute y into equation number 2. So I'm going to start by recopying the equation. So we have x minus y minus 2 equals 0. Okay, and then I know what my y value is, so I can replace it in the spot of y. So I get x minus 1 minus 2 equals 0. I do have some like terms here that I could put together, so I could combine negative 1 minus 2. So negative 1 minus 2 is negative 3. Then I can take my negative 3, bring that over to the right-hand side, which would give me 0 plus 3. So I know x has to be equal to 3. So therefore, my point of intersection for this linear system is located at 3 and 1. Remember that your x value has to come first, followed by your y value. Okay, just to kind of finish things off, what if you were given a set of linear equations? Okay, if you look at both of the equations, neither equation is in the format of y equals mx plus b. And then if I tried to figure out which equation would be the simplest to isolate or rearrange, and I scan all my numbers, the first equation's got a 2 in front of the x, it's got a 3 in front of the y. The second equation has a 3 in front of the x and a 4 in front of the y. So neither equation has a variable, either x or y, where there isn't a number in front of it. Okay, each variable is attached to a number. So we have no choice. We've got to work with one of them. And we're probably going to have to end up doing a little bit of dividing as well to get rid of the number that is in front of the letter. So when I scan the two equations, if I look at equation number 2, I notice that I've got numbers of 3, 4, and 9. So 3 divides nicely into 9, but 4 doesn't really divide nicely into 9. So I know that if I try to divide out some numbers with the second equation, they're not going to divide nicely, and I'm going to end up with some fractions. Remember, fractions are not the end of the world, but if we can avoid them, let's try to avoid them. If I look at equation number 1, however, I notice that 2 can be divided into 6 evenly, and 3 can also be divided into 6 evenly. So I have a little bit of a better chance with equation number 1 of getting just a couple of fractions. Not every number is going to work out to be a fraction. Again, because you've got numbers attached to both x's and y's, it really doesn't matter which equation you choose to isolate. Sometimes you're not going to be able to escape fractions with these types of systems, and you really have no choice. You're just going to have to pick and choose. I'm going to choose to rearrange or isolate with equation number 1, and I'm going to switch it up this time, and I'm going to choose to isolate for the letter y. So if I want to isolate for the letter y, that means I need to take this 2x and bring it over to the right-hand side. So if I were to do that, I would be left with negative 3y equals 6 minus 2x. And I can't just leave it like this because yes, I have isolated for the letter y. I've gotten the y by itself on the left-hand side, but I also need to get rid of the negative 3 that is attached to that y. So that means that I'm going to have to divide every single term by negative 3. So if I were to do that, that would leave me with y equals, and then I've got 6 divided by negative 3, which is negative 2. And then I've got negative 2 divided by negative 3. So I know that 2 over 3, or 2 divided by 3, is not going to divide nicely. I cannot leave it as a decimal, so all I can do is leave it as a fraction in lowest terms. Okay, I do know that 2 negatives make a positive, so this is going to be positive 2 over 3. So here is my equation that is isolated for the letter y, and I'm going to number it as equation number 3. So I know that y is equal to negative 2 plus 2 over 3x. So that tells me wherever I see the letter y in equation number 2, I'm going to replace it with negative 2 plus 2 over 3x. All right, so we've chosen to substitute equation 3 into equation number 2. So I've recopied equation number 2. So I'm going to go ahead now and substitute. So in the place of the letter y, I'm going to stick in my equation number 3. Okay, my next step is to simplify, and I'm going to have to distribute 4 into this bracket. So we have 3x plus 4 times negative 2, which is a negative 8. So I'm actually going to change the sign, and I'm going to write negative 8. And then we've got 4 multiplied by 2 over 3. So you could go ahead and put that into your calculator if you're not comfortable multiplying fractions on your own. So 4 times 2 over 3 is going to give you an improper fraction of 8 over 3x. So we've got 3x minus 8 plus 8 over 3x all equal to 9. So we could choose to keep solving as is, like we've normally done in all of our previous examples, or we could try to make the math a little bit easier for ourselves and get rid of that fraction. So when I look at that fraction, I see that the denominator has a 3. So I'm going to multiply every single term in the equation by 3. And that's just going to help me get rid of the fraction, give me all nice whole numbers to work with. So if I start from the left-hand side, 3 times 3x is 9x. 3 times negative 8 is negative 24. 3 times 8 is 24. 24 divided by 3 is 8. Still has an x attached to it. And that is equal to 9 times 3, which is 27. So now we have a much simpler looking equation that has no more fractions. So now I'm going to collect like terms. So I've got a 9x and an 8x that could be put together. And I've also got a 24 that I could choose to bring over to the right-hand side. So 9x plus 8x is 17x minus 24, which is equal to 27. I'm going to bring the 24 over to the right-hand side where it will become a positive 24. So I've got 17x, and then I have 27 plus 24, which is 51. And then to isolate for x, I'm going to divide both sides by 17. And if I do that division, 51 divided by 17 gives me 3. So here's my answer for x. And now it's your choice. You can take x and plug it back into equation number 1, equation number 2, or equation number 3. So I'm going to choose not to use equation number 3, only because it does have a fraction in it, and I don't want to work with fractions again, so I'm going to stick with either using equation number 1 or number 2. So I've chosen to sub x into equation number 1, so I'm going to recopy equation number 1, which was 2x minus 3y equals 6. In the place of x, I'm going to put in my answer, which was 3. 2 times 3 is 6, minus 3y, which is equal to 6. I'm going to bring this 6 over to the right-hand side. So that's going to leave me with negative 3y equals 6 subtracted by 6. 6 subtracted by 6 is 0. And then I want to isolate for y, so I'm going to divide both sides by negative 3, which gives me 0. So therefore, my point of intersection is going to be 3 and 0. Solving linear systems by substitution does require a lot of practice until you get very comfortable not only with isolating certain equations, but also knowing how to substitute one equation into the other. The more practice, the better you'll get, and once you've mastered substitution, you'll be ready for our next method in our next lesson, which will be elimination.